Just to let you know, I think we just determined that the video has a lag of somewhere between 2 and 5 seconds. So please bear with me as the slides change. And I think the audio might have a lag of a few hundred milliseconds. So, but yeah, my name is Brandon Rohrer. I work for Microsoft as a senior data scientist based in Boston. And I'm going to talk today on closing the loop, a scalable ensemble reinforcement learning algorithm for the Internet of Things. The Internet of Things is a fancy phrase for when we have sensors that are providing information to our systems that then need to take actions. And it poses a really interesting technical problem. As a motivating example for this problem, consider a large office building with a lot of offices in it. Each one has an independent thermometer, thermostat, and temperature control. And right now, the way that all of these are controlled is a facilities manager decides that every room should be at a certain comfortable temperature, and that's the default. But you can imagine every day on the 3rd floor in an office, someone walks in and turns the temperature up by 3 degrees. And every day on the 12th floor in another office, someone walks in and turns the temperature down by 5 degrees. Those adjustments to the desired temperature are useful information. Those are sensors. The ability to take all of that information from the building, funnel it somewhere, make a smart decision based on that, do something similar to what a human would do, and anticipate where to keep the temperature, perhaps reorganize offices so that hot offices and cold offices are in one block and save money, save energy. These are things that could be done, but right now they're not being done. And one of the barriers to this is having an appropriate learning algorithm for this type of problem. So I'm going to talk about one. In addition to building and facilities, there's, as I mentioned before, heating and air conditioning. There's also lighting. And then there's also obvious applications in security systems and surveillance systems. You have decisions to make, which is, do I trigger an alarm or not? Do I pan and tilt a camera in a certain direction or not? And you have lots of sensors, motion detectors and floor pressure sensors. Similarly with advertisement and marketing, the biggest example that a lot of us are familiar with here are when I present a web page to a viewer, what ad do I put at the top? What ad do I put at the side? Or if I have a list of ads, which do I put at the top? This is a decision that has to be made many times and very quickly. And whether or not the person clicks on an ad or mouses over an ad provides information. And so all of that information can be fed back and then used the next time that decision needs to be made. With robotics, unmanned aerial vehicles are being used in more and more applications now. There has been talk of using them to deliver food and packages, but at present they're being used to inspect buildings and structures. They're being used to gather aerial photography of cities and of farms. And the ability to take information in from a swarm of these, process it and respond to it in real time would be very valuable. And then finally, there are entertainment applications for this. Gaming is a great one. In most games, there are AIs, there are non-player characters that need to behave in a believable way. Often this is pre-programmed, or at least the way in which they respond to the player is pre-programmed. But in some cases, it might be desirable to have these AIs learn. and to have them become increasingly more sophisticated. So this is just a few of the ways in which solving this problem can make lots of money. To be honest, the reason that I'm interested in it is because it's a really interesting problem. My background is in robotics, and being able to solve this problem well would make it possible to have very sophisticated robots. So to dive into the technical side of it, reinforcement learning is a branch of machine learning. It's originally based in behavioral psychology. There's the observation that if you reward a rat or a dog or a human consistently for doing something, then they will tend to do that thing more and more. And similarly, if you punish someone for doing something, they will tend to do that less. So this same idea has been applied to machines. If you look at the diagram over on the right-hand side, you can see a very simplistic view of a reinforcement learning system. There is an agent, and the agent you can think of as an animal or a person or a thing whose job it is to make decisions, specifically to choose actions. So in a discrete time system, at each time step, it chooses an action or actions. Those have some effect on the world. And then this agent also has sensors that reflects back to it the state of the world. And then the cycle begins again. It chooses more actions and senses the results. Now, what makes this a reinforcement learning system is that there is also a reward signal. So the agent is specifically wired or pre-programmed to interpret some states as being rewarding. So for instance, most mammals are wired to respond positively to sugar on their tongue. And that's a nice little trick to get us to eat things that are high in calories, that is good for survival. But it doesn't have to be sugar. You can have an agent that is rewarded for anything. It can be rewarded for using less energy when heating a building. It can be rewarded for, in a video game, keeping a player engaged longer. And so once you define that reward signal, then it's the agent's job to choose actions such that that reward is maximized. This is different than regular supervised learning in a few ways. For one, it doesn't need any data to start. It can just start choosing actions and sensing the results and learning from them. It doesn't need a large collection. In a way, each choice of an action is its own small experiment. So the agent is conducting many, many micro experiments on its world and compiling the results into one unified view of what's going on. Another really nice part is it doesn't require any ongoing human participation. So once you set this up, the agent is autonomous, and it can learn, and as much as the design of the system allows, it can refine its performance and get better and better. So just to give you a little bit better idea of what I mean, I'm going to talk about one such reinforcement learner. This particular algorithm is something that I designed for use in robotic applications. It's not a mainstream reinforcement learning algorithm. There are many, and there are lots of work being done on it, and there are many more that have not been tried. Large technical areas that are completely unexplored. So this is a very new and still very undeveloped area in general. But this is just to give you an idea of one specific algorithm so that you can see what I'm talking about and what types of things a reinforcement learner can do and how it can help in solving the Internet of Things problem. So this particular reinforcement learner is called Becca. It is a hybrid unsupervised learner, and then it has a reinforcement learner in tandem with it. The unsupervised learner takes in sensory observations and builds up a hierarchy of features. It is not, well, it is a type of deep neural network. I'm not going to talk more about it, it's a separate topic. But all we need to know about it for the purposes of this conversation is that it creates a set of features out of the observations. These features are then passed to the reinforcement learner, and the reinforcement learner can take these and start to learn which patterns of features correspond to which actions it should choose. And if you're interested, all of the code for this, it's written in Python. It's all available on GitHub publicly. This is open source if you'd like to inspect more deeply or follow up with documentation. So the things that a reinforcement algorithm does, as it gets a reward, it updates its estimate for each feature action pair. So to use a really simple example here, imagine you're in a room. The room is painted green. There's a door on the left and the door on the right. So in this case, feature is green room, and then your choice of actions are open the left door, open the right door. So if I'm in the green room, I open the left door and I go into that room and there's $100 sitting on the floor. That would be the reward associated with the feature action pair of green room, left door. And so each time the algorithm goes through, it needs to update this estimate, because it might be when it goes through a green room, like half of the time it opens the left door and there's nothing there. And the other half of the time there's $100. And so on average it realizes that it can expect a $50 reward for opening that left door in the green room. So the next thing that the algorithm needs to do is, based on its accumulated estimate, it needs to choose the action that's likely to result in the highest reward. So once again, when it finds itself in the green room, it needs to look back on its experience and decide, now, do I expect a higher reward from the left door or the right door? And then based on the fact that it's in a green room, it can make that decision. There's one other element that's important, and this is using curiosity to perform some exploration. So for instance, if it's in the green room and it knows that it can expect $50 by opening the left door, but it's never tried the right door, it might be worth its while. It's possible that there's nothing behind the right door. It's possible there's $1 million. And so it's nice to have a little bit of motivation to try the thing that you're not certain about. So this algorithm does that. It also tries the thing that it hasn't tried in a long time. So if it opened the right door once and there was nothing there, and twice and there was nothing there, and then it waits for a very long time, it'll eventually try the right door again, just to make sure that the world hasn't changed when it wasn't looking. So here's a simple example. If you look at the grid on the right-hand side and the bar above it, the bar above it is a world. It's a very simple 9-state world. An agent can occupy any one of those 9 states. It can step to the left, it can step to the right. If it steps so far to the left that it reaches the end, it will actually circle back around. So this is a ring, but it's unrolled here into a strip. There are 9 different actions that an agent can take. It can step 1 state to the right, or 2 or 3 or 4 states to the right. Similarly, it can step 1, 2, 3, or 4 states to the left, or it can do nothing at all. And so if you look at how the states are numbered, the numbering scheme down at the bottom of the screen, 0, 1, 2, 3, state number 3 is rewarded, and state number 8 is punished or penalized. And so it's obvious that an agent in this world would want to move very quickly to state 3 and stay there forever. That would be the optimal thing to do. The one quirk, the one kink in this world that makes it a little bit more challenging is that on about 10% of the discrete time steps, there are random jumps, and the agent ends up in a randomly selected state. And so it has to keep making its way back to the reward state. So if you look at the grid, you can see the actions are represented. The left and right steps are represented by icons there, and they're also numbered 0 through 8. This 9 by 9 grid is the entire feature action space. Every pair of feature and action is represented by one square on this grid. So we'll step through what the algorithm does when operating it. The first step that we talked about was updating the reward. So for each feature action pair, we want to take the estimate and step the old estimate toward the observed value. Now we only step a fraction of the way. This allows us to filter out the effects of variability and noise and perform a stochastic, or to filter out stochastic processes. And it's also important to note that all the other feature action pairs are unchanged. It's only the one that's currently active. This is an incremental algorithm, which means that each time through it does the same thing. Each time it gets a new data point, it performs the same operation. So if we step the estimate 1/10 of the way from the old estimate to the observed value, then you can show that within 42 iterations, you get to within 1% of a steady state value. So it takes, you have to experience something a number of times before you get a good estimate of what it's likely to do. So in this case, our agent is in state 5, position 5. And it moves 2 positions to the left, and it ends up in the reward position. So in order to map this onto our feature action space, we select out the column that represents position 5, and we select the row that represents 2 steps to the left. The square that isolates is the feature action pair corresponding to that movement. And then we increment it. We get it closer to the reward. We say, hey, that was a good thing, and I want to note that. The next time I'm in this position, that's an action I want to take. So here's some cleaned up version of the Python code, just to show that the code behind this is very simple. It's just some arithmetic. That matrix, the feature action matrix, is often called a value function, and mathematically it's often referred to as Q. So the indices of the Q matrix are just given by multiplying the binary vector representing state by the binary vector representing action. That'll return a matrix of zeros that has a 1 at that state action location, the feature action pair that's active. And then the error in the reward or the return that's observed is just the observed return minus the expected return. And then the rate, we mentioned that 1/10 works well. And when incrementing, the Q matrix is just incremented just the indices that are relevant are incremented by the delta return by the rate. So pretty simple algorithmically. The next major thing that the algorithm needs to do is to choose an action. So now this time around, it's got to decide what it is it wants to do. So in this case, our agent has already been alive for a while and made a number of decisions, and you can see the estimate of the Q function or the value function down below. White squares are rewarded, black squares are punished. So we want to find a white square to use. In this case, the agent is in state 0, so feature 0 is active. This then it uses to perform a weighted average across all the actions. In this case, the weights are trivial. The weight on feature 0 is 1, and the weight on everything else is 0. And so it isolates the one column of values. And then the job is easy. It's simply to choose the action that has the highest reward associated with it. And if you look there, it might be 2 steps to the right. It might be 3 steps to the right. They look pretty similar. But for the sake of the demonstration, we'll say it's 2 steps to the right. So this then becomes the action that gets chosen to be executed in the next time step. This also includes, I don't spell it out here, but it includes whatever curiosity has been built up. If there are options that have not been chosen or have not been chosen in a while, that will be added in to this value function for this selection. So in this case, the action 2 steps to the right is executed, and it gets the agent closer to the reward, but not all the way there. So we can see this is a young agent. It hasn't trained very much yet, so it hasn't yet identified the very best thing to do in every situation, but it's already starting to learn good things to do. And again, here's the simplified Python. The expected reward or return by action is just a weighted average of the return, where the weights are the feature activities. And then the action is simply the row that has the maximum value of the return, expected return. Here's added in the code that's associated with curiosity. And I won't step through it in detail, but you can see it also is not very complex. It's related very much by the count, the number of times that feature action pair has been active. So the more times that something has been tried, the less curious the agent is about it. So some quick notes on the computational complexity. You can see from what we've done so far, all of the operations are on this Q matrix, and it has n states by n actions. However many states and actions you have, that determines the size of your matrix. And the operations that we've done are have not been, they've all been linear. They've all been of the order of the size of the matrix, nothing too insane. Computationally speaking, that's really quite reasonable. It's not exponential, so it's something that scales well. Another observation I'd like to make is that a lot of the computation that we did was essentially one row at a time. There's the indexing, and then once we decided what our state or what our features were, then the operations were largely on just those columns. So because we're only updating one feature action element at a time. There's no interaction between states. We're treating them all independently. This actually behaves as an ensemble of small reinforcement learners, one for each state. And so that's why I stretch and I call it an ensemble learner in the title. But what makes this really nice then is that this is easily distributable. If you have many states and actions, a very large and complex system, which the Internet of Things promises to give us, then there's no reason that you can't take this and distribute it across many compute nodes and a lot of storage, distributed storage space. And that right there is what makes it really feasible to tackle large and complex problems with this approach. So in this case, if you run the agent a little farther, we can watch the evolution of the value function. So this is an agent that's slightly more mature, and you can see the bright spot in the value function is in the top row in state 3. And that makes a lot of sense. That's the agent saying, if I'm in state 3 and I choose the no action option, then that will give me a really good desired result, which is a nice thing to learn, pretty trivial. And then the more it learns, you can step it through another few epochs. And by this point, the agent is pretty mature. And you can see there are some very well-defined white squares and also some faded black squares. The reason the black squares aren't as well defined, by the way, is those correspond to punishment, and the agent doesn't spend the time reinvestigating those to learn just how bad the punishment is. Once it realizes that it's significantly worse, then it stops bothering it, which is a nice property to have. But in this case, if you look in the 0th column, state 0, you can see that the white square there corresponds to the step 3 squares to the right, step 3 states to the right, which is exactly the action that you would need to get you to your reward state. You can do a similar exercise with all of the rest of those white squares and realize that those white squares demonstrate an optimal policy. No matter where the agent jumps, it will return to the reward state in one time step and stay there, which is kind of nice. Now, this is a very simple example, almost trivial, but it's really useful for illustration. So I applied it to a slightly more complex example. This is a simple robot. There's a video associated with it. Don't start it just yet. Let me give a brief introduction. There's a simple robot you can see here. It looks like the Roomba, if you've seen one, a robotic vacuum cleaner. It's round, essentially two-dimensional. This robot, it's rewarded for catching that little blue ball. And the way it catches it is it touches it right between the eyes. As if it had a mouth, it would be like eating it. The robot has a number of sensors, including an array of 16 proximity sensors around its body. It can tell where the wall is. It also has an array of 16 range sensors. It can tell how far away the ball is and in which direction. It can make movements forward and backward. It can spin left and right, each with 4 different magnitudes. So that's 16 different movements that it has available in all. Now, if the audiovisual setup is, everything has gone smoothly, there should be a video available there on your end.
Brandon, we've got this video, so I can just, in order to avoid delays, I can run it right now on the screen, okay?
Please, that would be great.
Just a second, so we are running it
It should last about a minute. Let me know when it ends. I won't be able to see it, but I will mention some things as it runs. Oh, and be sure and turn off the audio from the video. So as the robot begins its life, it's exploring. It doesn't know what to do or how to proceed in order to catch the ball. You can see it sitting still sometimes, making tentative movements, and trying to figure out what movements result in a reward. As it gains experience, it gets a little bit better. It'll step in the right direction, but often it'll miss. It won't catch the ball every time. And then you can see what happens as it spends more and more time training. Incidentally, the training times listed there are simulated times, not wall clock times.
So we are at 36 hours now.
Okay, good.
5 days.
So you can see now that it's actually becoming quite reasonably proficient. And in terms of agent learning, a human or an animal, 5 or 12 days is really not.
Yeah, we are 12 days.
So this is just a slightly more sophisticated example, but demonstrating that with not just 10 sensors, but scaling it up to 100 sensors and closer to 20 actions, it can still learn. And then the goal is to scale it up to millions of sensors and millions of decisions. So the video wrapped up successfully there, and I'm back on the screen.
So the video is over and your screen is projected.
All right, fantastic. So that's just a slightly more complex example, just to show that it works on something that is not utterly trivial. So I just wanted to step back now. That concludes the investigation or the presentation of this particular algorithm. But it's just one example in a very large space of potential solutions to this problem. But just to get you thinking and motivated and hopefully a little bit excited, I want to take a step back briefly and look at the implications of, or what we can do to solve this problem. So closing this loop, getting a human out of the way so that the learning can happen automatically. The sensors feed in, the algorithms update, new decisions are made, in essence, new experiments are performed, and the cycle continues. So one of the big things is to move toward incremental algorithms in these applications. There's a strong tendency, a lot of literature and a lot of great libraries around batch algorithms where you have all of the data to start with. And those will always be useful. But in this application, I believe we need something else, and that is taking incremental algorithms, of which there are many and good ones, and making sure that we have good implementations for those as well. When you have an incremental algorithm, it allows for constant adaptation. So if you don't want to make the assumption that your world is static and that nothing really changes, then an adaptive algorithm is a highly useful thing to have. So this also, closing the loop, in order to do it, we will have some work to do still with integrating cloud machine learning with sensors and actions both. So Microsoft has a tool called Azure Machine Learning, which is part of a larger suite of tools called the Cortana Analytics Suite. And it contains tools for bringing in data, processing it, sifting through it, and learning from it, and then sending those actions back out. This is the type of thing that that'll be necessary to really attack this Internet of Things problem. As I mentioned, a big benefit of this is the human isn't necessarily in the loop, and that the number of times you can cycle through this isn't limited by human response time. So that was all of the material that I had prepared. I'd be happy to field questions in any remaining time.
Hello, Brandon. Thank you for the presentation. It was really interesting. And I would like to ask you, how do you actually use reinforcement learning in Microsoft, and like which applications do you do for that?
Let's see. So right now, reinforcement learning is not widely used in Microsoft, but there's a notable exception to that. There is a group out of New York led by, let me see if I can remember his name. I'm blanking on his name. Hopefully he'll come back. But John Langford, who got well known in machine learning circles by working on a framework called Vocal Rabbit. And he and his team have adapted that into something called multi-world testing, which is in essence a reinforcement learning approach. And they've actually been using that to choose news feeds for Bing users. So to choose which news articles are going to appear at the top of the feed and so forth down the list. So this is something that's relatively new to Microsoft, and it's something that I'm actively evangelizing for within the company.
Okay, so the question at the back.
Thank you for the presentation. You mentioned about unsupervised learning algorithm, but just today guys told us about, as I mentioned, deep reinforcement learning. I just want to ask you, what is the main difference between them and which one is better? Thank you.
Deep reinforcement learning?
Yes.
So I don't know exactly what was presented yesterday, but I have heard several references to deep reinforcement learning. One of my friends actually is working on it, and so we've talked about it. My understanding is what it means is that there's a reinforcement learner that is paired with a hierarchical unsupervised learner, like a deep belief network or a convolutional neural network, so a deep learner. And so, as I mentioned when I was introducing Becca, if you read in all of your sensor information and first pass it through a deep neural network to create features, and then pass it to your reinforcement learner, that makes it a deep reinforcement learner. So actually what I talked about today was a deep reinforcement learner. I just didn't talk about the deep part.
Okay, so the next question.
Thank you for this awesome presentation. My question is simple. The example in the presentation shows us that this learning type is very suitable for game AI. So, and Microsoft has a game department, and maybe they use some things for the games. No? Maybe you know some examples in not Microsoft games which uses this pattern to train gaming AI.
You know what? I wish I did. I actually have not spoken with the game department. I think Halo is the big winner there, big game. But I haven't spoken with the people who do the AIs there. That's on my list of things to do.
Another question on the, okay, sorry.
Another question. So first of all, I want to thank you for the great presentation, and then I have a question about the curiosity factor. I find that the idea is great, but there are some, well, issues. I think there are some issues with it. Suppose there is a cleaning robot like Roomba or something, and it's exploring the room, finding the path to the areas that are to be cleaned, and it decides, hey, I haven't tried running down the stairs in a long time. So how to safeguard the robot from such decisions?
Yeah, so that's a really excellent point, and you're exactly right. As it is currently, as I described it to you, I mean, if you've ever observed a small child, you've seen a similar thing. You know, there's nothing that will prevent them from doing something that's potentially catastrophic, and that's the nature of the agent. And so, in order to prevent that, in a in a theoretical sense, it needs a watcher or something to prevent it. So, for instance, with the Roomba, you know, there's you put up barriers or you put up little markers of where the top of your stairs are. In a practical sense, I would expect that any robotic system, for instance, that I would engineer to use this would have low-level guardrails. Like there would be things hardwired into it that say, hey, don't do this. For instance, if it's a robotic arm, you know, don't hit yourself. And maybe certain pressure sensors where you never exceed a certain pressure, that type of thing. But this learning algorithm is all about, it basically assumes that the world is a friendly padded cell and that any action might be unpleasant, but won't be catastrophic.
Okay, so yeah, another question.
Question not related to robotics. In your first answer, you mentioned that your colleague use this technique to some kind of news ranking system. So maybe you have plans to incorporate this technique of learning inside Cortana. For example, to learn it, to anticipate some of our decisions and to make it a more sophisticated assistant. Do you know something about this?
So I'm not aware of what strategies and what agent design the Cortana team is doing either, unfortunately. The downside of being in such a large company is that I only ever get to see a very small part of it at once. But I sincerely hope that they do end up doing something like that. You can imagine as a Cortana user, if you have to correct Cortana in the same way every single time, it wouldn't feel very smart. You know, it would be nice to at least in some very simple ways have it anticipate your requests or anticipate the tasks that you want it to do. And so I'll be looking for opportunities to interact with the Cortana team, but I haven't begun that yet.
Okay, I think that was a good question. So, any more questions in the room? No? Okay, so Brandon, we'd like to, on behalf of the audience, I'd like to thank you for the great presentation. Thank you for your time. And yeah, we'd be happy to hear you.
Thank you very much. I really appreciate the invite and I enjoyed speaking.